Hi, and welcome to this video on early scientific laws leading to modern atomic theory. In this video, I'm going to be discussing some very basic scientific laws that were formulated over 200 years ago. And these laws were the first attempt at trying to explain the behavior of matter. And ultimately, these laws led to atomic theory that we still follow today. So specifically in this video, I'll be discussing the law of conservation of mass. I'll talk about the law of definite proportions. Then I'll talk about the law of multiple proportions. And then finally, I'll show you how these three laws finally led to the formulation of atomic theory. When we consider the composition of matter, odds are we're very familiar with the idea of the atom. In fact, I would wager that we've all learned about the atom as far back as grade school. And so if I were to ask you what happens when we take a sample of silicon and break it down into its smallest components, what would we find? Well, we know already that we would find atoms of silicon, individual units of silicon. And in fact, now we have the technology that allows us to actually image individual atoms and see that they truly exist. However, we have to remember that the concept of the atom hasn't always existed. And in fact, this theory of the atom wasn't proposed until the early 1800s. And before that time, scientists really didn't have much of an idea as to what matter was composed of and really didn't have a systematic understanding of the behavior of matter. So in this video, what I'm going to be trying to do is I'm going to show how these three basic laws led to our current understanding of what matter is composed of. So let's start off with the law of conservation of mass. Now, the law of conservation of mass was first proposed by Antoine Lavoisier in 1789, and it simply states that in a chemical reaction, matter is neither created nor destroyed. So if I were to do a reaction between sodium metal and chlorine gas to form sodium chloride, which is table salt, and if I measured the amount of the material before the reaction takes place and the amount of material after the reaction takes place, I would see that the mass of everything is being conserved. I wouldn't be creating more mass than what I started with, and I wouldn't have less mass than what I started with. So here we're seeing that mass is being conserved in any chemical reaction. Now, the second law is called the law of definite proportions, or it's also known as the law of constant composition. Now, this law was proposed first by Joseph Proust in 1797, and it states that samples of a given compound, regardless of source or method of preparation, have the same proportions of their constituent elements. So, for example, if we had 100 grams of pure water and we decomposed it into its constituent elements, we would see that there would be 89 grams of oxygen and there would be 11 grams of hydrogen. And the mass ratio of the oxygen to hydrogen would be 89 grams of oxygen divided by 11 grams of hydrogen, which we could then simplify to 8 grams of oxygen for every 1 gram of hydrogen. So we see that for water, it has a mass ratio of 8:1 oxygen to hydrogen. And what the law of definite proportion states is that if in order for a sample that's suspected to be water, in order for it to be water, it must, regardless of its source and regardless of where you got it from or how you made it, it must have an oxygen to hydrogen mass ratio of 8:1. And if that sample of matter does not have that proper ratio, it's either not water, or if it is water, it's contaminated and not pure. A big consequence of the law of definite proportion is the fact that matter or the composition of a compound is not haphazard and it doesn't change from sample to sample, providing that it's pure. Now, the third law to discuss is the law of multiple proportions, and it was first proposed by John Dalton in 1804. And it states that when you have two elements, A and B, that form two different compounds, the masses of element B that combines with 1 gram of element A can be expressed as a ratio of small whole numbers. Now, the wording of this law is a little challenging, so it's easier to really demonstrate it by using the following example. We have two different compounds that are containing only phosphorus and fluorine. We have 100 grams of compound 1, and if we break it up into its elements, we find out that compound 1 has 35.21 grams of phosphorus and 64.79 grams of fluorine. We also have a second compound, compound 2, and 100 grams of that. It also contains phosphorus and fluorine. However, it only contains 24.59 grams of phosphorus and 75.41 grams of fluorine. In order for us to see whether these two compounds fulfill the law of multiple proportions, what we want to do is compare the mass ratio of the fluorine to each other in the two compounds. But in order for us to do that, we have to make sure that the phosphorus in both compounds is the same amount. What we're going to do, therefore, is we're going to re-express the different phosphorus and fluorine ratios per 1 gram of phosphorus in both compounds. So for example, with compound 1, in order to re-express this ratio of phosphorus to fluorine, for every 1 gram of phosphorus, I'm going to divide both of these numbers by 35.21, which will lead to 1 gram of phosphorus and therefore 1.840 grams of fluorine. Now I want to do the same exact thing to compound 2, and I want to re-express the phosphorus to fluorine ratio per 1 gram of phosphorus. But this time I'm going to divide both numbers by 24.59, and that's going to lead to 1 gram of phosphorus for every 3.067 grams of fluorine. So now we have the composition of both compounds, and both compounds have the same mass of phosphorus. Now we can focus on the ratio of the fluorines and see if they're going to be in a small whole number ratio. And we can take a look at the 3.067 grams of fluorine, which is coming from compound 2, and we're going to divide that by the fluorine from compound 1, which is 1.840. We do the division and we see that the fluorine is present in a 1.667 to 1 ratio. If we want to express this ratio in whole number, what we need to do is multiply the top and the bottom of this ratio by 3. And that's going to leave us with 5 to 3 ratio of fluorine within these two compounds. Notice when you have both of these compounds and you have the same mass of phosphorus in both compounds, we see that the fluorine is indeed in a small whole number ratio, and we're seeing that the law of multiple proportions actually does hold in this scenario. Now you might be asking yourself, what if I wanted to compare the ratio of the phosphorus and have the fluorine be the element that's not changing? Well, in this slide, you can take a look at my calculations, and you can pause the slide, and you'll see that I did exactly that. And notice how at the end, we still get a whole number, a small whole number ratio of phosphorus in a 3 to 5 value, just like we got in the previous slide. So the law of multiple proportions is still holding here, even though we looked at the other element. Okay, so now that we've looked at all 3 of these laws, now let's take a look at the consequences of these laws and try to understand how we can explain these behaviors or the observations from each of the 3 laws with one consistent explanation. So with the law of conservation of mass, recall the law, there's no change in matter. So whatever is making up the matter has to be present and accounted for both before and after a reaction takes place. Another way of stating this is that in a chemical reaction, matter is not coming out of thin air, it's not being destroyed into nothingness, and it's not being formed from nothing. So whatever is making up the matter has to be there the whole entire time throughout the process. Now for the law of definite proportions, what we see is that compounds are made by a combination of elements in fixed and reproducible amounts. So a sample of a compound is not going to be haphazardly composed of different elements in different times or in different samples. If a sample is supposed to be a certain compound, its composition has to always be fixed and known. Now for the law of multiple proportions, what we see is first is that matter is made up of discrete quantities of elements. And the idea that compounds are being composed of discrete amounts of the elements is really important and is really hinting towards the concept of the atom. But we also see that compounds are composed of these discrete elements combining in small whole number amounts. So how can we explain these consequences with one view that allows us to understand why these laws actually exist in the way that they do? Well, the only way that the scientists were able to come up with one consistent description was explaining that matter is made up of particles. And if we view matter being made up of individual particles, we can then explain why these three laws actually exist and behave the way that they do. So for example, with the conservation of mass, if matter is made up of particles, well, those particles aren't going to go anywhere. They're always going to be present during the chemical reaction. So whatever particles we're starting off with have to be present after the reaction takes place. And this particulate view of matter can also explain why the definite proportions law and the law of multiple proportions also exists. So what we see is that the only way that we can explain these three laws is by the concept of the atom, which was then soon proposed by John Dalton a few years after the law of multiple proportions was established. Okay, so now that you've watched this video, you should be able to fully express the laws of conservation of mass, the law of definite proportions, and the law of multiple proportions. And you should also be able to understand their ramifications, especially when we're talking about the composition of matter. You should also be able to apply the laws mathematically and be able to do calculations based on these different laws. And finally, you should understand how the theory of the atom was a necessary outgrowth of the findings of these laws. Okay, so hopefully you got something out of this video. I hope you enjoyed it, and I look forward to seeing you in future videos. Bye for now.